Hi, and welcome back. So last time we had talked about a couple of examples of using group by and summarize. And if you remember, it's sort of like a zooming in on different areas within a spreadsheet and compacting or summarizing the information within that area. So we could do things like, okay, well, we want to summarize these particular columns within these particular groups, if you will. So say find the average systolic blood pressure differentially for the treatment group versus the control group, or find the distributions of heights and weights for the males versus the females. And so this is the whole point here, that a lot of times we have subgroup analyses. We want to look at what's going on in our data that we believe, yes, there may be an overall effect within the data, but usually we're interested in studying subgroups. That's one of the kind of the main ideas in statistics, is to say, okay, well, can we measure to find out if this group is different from this group, and by how much and in which way? Now, what we hadn't covered, we stopped right before we got to this section, was grouping by multiple variables. And the reason that I wanted to talk about this a little bit differently, and then it's going to be a little bit shorter. We'll talk about this, and then we'll move straight into talking about joins. Um, is that grouping by multiple variables allows us to roll up nested groups. So the two main examples of times that I deal with rolling up data is if I have geographically nested groups or if I have temporally nested groups. So I give an example here of a temporal nesting where the day is nested within the month, which is nested within the year. And so what we can do is we can summarize by the day within the month, and then we can summarize by the month, and then we could summarize by the year. And that would allow us to sort of like collapse in, if you think about like the Russian nesting dolls, if you will, that each chunk of the data is inside of another chunk of data. Another thing that we can do is if we have geographic level data where you have data at census tracts, and those census tracts are all contained within counties, or perhaps if you've got another data set, you've got census tracts within metropolitan statistical areas, and then those counties or metropolitan statistical areas are contained within states. So you have this nesting of geography where you've got the smallest level of granularity of the geography inside of a larger level of granularity of geography inside of this super level of granularity. And the reason that you may want to do something about that, something like that, is if you have public health data where there are different types of policies that could impact the people of interest, or the disease of interest in the particular area. So let's say that you've got a state level policy for this particular disease, and it's different across multiple states. But then within a particular state, you may have even county level interventions. An example that I can think about is if you're dealing with HIV incidents. The state of Florida has, like, I think, average levels of HIV incidents, but South Florida in particular has incredibly high rates of HIV incidents. So you wouldn't want to just say, okay, well, we want to analyze South Florida independently because there are policies that govern the entire state of Florida. And so you have to say, all right, well, we need to account for the fact that South Florida is special. So maybe even down to the neighborhood level or census tract level or zip code level, that you've got different pockets of HIV incidents. But then you also say, okay, well, are there county policies in and how the public health interventions and access to care and resources? So you've got like the census tract level where you can say, okay, can we get access could a person get access to needle exchanges? Could a person get access to PrEP? Could a person, like, how far does a person have to travel to get access to a care provider? And that could be at the very granular census tract level, or perhaps even zip code level if it's a very, very compact zip code, or the neighborhood census defined place level. So there's a lot of different geographical levels that are very small. And then you can say, okay, well, now there's county policies that are dealing with how the public health infrastructure interacts with and attempts to alleviate the disease burden of HIV. But then you've got policies for the entire state of Florida, and those policies could be different from Alabama, different from Georgia, different from South Carolina, our neighboring cities. Or perhaps you want to compare similar states who say, okay, well, the other large states in the United States, large states, huge metropolitan areas. So we're going to compare Florida to California to Texas to New York or something like that. And so there's ways that you can roll up the geographies there. And that's what grouping by multiple variables is all about. So right here, I give an example. We've grouped by the year, the month, and the day, but then we summarize. And as soon as we summarize once, it's going to roll up all of the day values. So there's 337,000 records, but now as soon as we group by year, month, and day, we only have 365 records because 2013 wasn't the leap year. And so this is the number of flights on each day. So January 1st had 842 flights, and then January 4th had 915, et cetera, et cetera, et cetera. We could then take the next roll up to roll up to the next level of granularity. So after the day, we could, if we wanted to, roll up to week, and that might be something that we're interested in doing. But realistically, all we would have to we'd have to use the mutate command to create a week indicator, but we didn't do that. So the next summarize that gets called. So notice I've got a per day data set. It's grouped by year, month, and day. And we've called one summarize. This summary gets us from 337,000 rows down to 365 rows because we've collapsed within the day. If we collapse again, now there's only going to be 12. We're going to have 12 records in this data set because we've grouped over all of the months. So we had started by grouping by day, and that got us down to 365. And then within the 365, we grouped by month, we get to 12. And so you see these are the records for the 12 months. And then if we group again, we get down to one record because there's 1 year in the data. If we had 2 years in the data, then this would be 365 times 2 number of rows because we'd have all the 2013 data, then all the 2014 data. This would be 24 rows because you'd have all of the months for 2013, all of the months for 2014, and this would be 2 rows. You'd have all of the flights, the 337,000 flights for 2013, and then all the flights for 2014. Okay, so basically the summary of this is whenever you have nested groups, that's when you want to use, I'm sorry, I scrolled too far. That's when you want to group by multiple variables if you have nested groups. All right, let's talk about joins. I want to spend the last, probably the next 5 or so minutes talking about joins. So, and I'm not going to spend a whole lot of time talking about joins because I am hoping to have a guest lecturer come in and talk to you about joins. And this person uses dplyr to do joins, dplyr and SQL to do joins in their work. And they do it all the time. They have gotten very good at this. And yes, I could teach it, but why not ask someone who literally does this as their job to come teach you joins? I'm just going to give you kind of the overview here. So joining, the whole point of joining is a lot of times you have data from multiple tables. So talking about the HIV data in the state of Florida, we could have data at the census tract level or data at the county level from multiple different data sets. So I've got a data set with all of the providers by the address of that provider. And so we use GIS to map the addresses to census tracts or census defined places or something. And so we would end up with one data set where we have all of the providers, like all of the people who could prescribe PrEP. Like, so they're a nurse practitioner, or they're a doctor, or they're a PA. They have prescribing privileges, and they could theoretically prescribe PrEP for someone. For those of you that don't know, PrEP is one of the drugs that can be used to prevent HIV transmission and I believe prevent you from getting HIV as well. So you've got what you could do is you would have one data set that has all the providers for the geographic locations, and then you've got another data set that has all of the that has all of the people with that are HIV positive in those locations. Well, those are two different data sets because the one for providers may come from a totally different database. The one for the HIV positive based on census defined places would come from the state of Florida from their protected health repository. It's called Merlin. And so obviously you need to be able to connect those data sets. Well, that's what the join functions are going to do. We have to make sure that in each data set, there's one column, sometimes two, but it's usually one column that match exactly between the two data sets. Okay. Now they don't have to be in the same order, obviously, and they don't even have to be the same number. It just has to be that there are values in this column over here called a key column. So there's values in the key column for the geography of the patients, and then there's values in a key column for the geography of the providers. And those values, there has to be at least one value over here that matches a value over here. And realistically, there should be tons and tons of values that map and crosswalk between the two. Okay, so that's what the joins are doing. You're going to for every single one of these functions, you're going to specify a column called by, and that is the name of the column that includes the key information. So I say, okay, this is zip code. This column is called zip code, or this column is called county, because one of the examples that we're doing in this class is we're going to be looking at food stamp data, and the joining column is going to be the zip code. Or this column is the census defined place, something like that, so that you would be able to connect the data sets together. And so what's going to happen here is you just specify the two different data sets. So maybe data set A is our patient data set, and data set B is our provider data set. And then we've got a column that can connect the two that's called the census defined place or the zip code. And so you say by equals census defined place or by equals zip code. Okay. And the way it works is left joins. So you're going to realistically, I'm going to just give you a brief example. Let me see. Give me 1 second. I'm going to see if I can find a diagram to show you. Okay, so sorry I had to pause. I literally just thought of this as I was going through this material. I'll have to add it to the lesson. But there's a data carpentry lesson here that gives a visual understanding of what the left join, right join, inner join, full join, et cetera, are doing. Okay, and so let's start with left join. This is usually the one that's going to be used. And if you need right join, you usually just swap X and Y. I don't think I've ever typed a right join before. But anyway, so left join, what you want to do is if this was our patient data, then all of the rows of the provider data that match a geography in the patient data would be preserved. So if I've got patients that are in these 5 census defined places, but I've got providers that are in 50 or 60 census defined places, then a left join, what I'm going to do is I'm going to say, keep the 5 records or the 5 census defined places that I'm interested in with my patients and go find or match the 5 records over here with providers. And if for some reason, so it would be like, okay, well, this row matches this, and this row also matches this, and this row matches this one, etc. So if I have 5 rows over here, a left join will mean that I have 5 rows at the end, and I'm going to fill out these rows from the provider data set. And if there's not a matching record from the provider data set, then that row is going to be filled out with NA. So that's the left join. Whatever data set that you start with, however many rows are in X, that's going to be however many rows are in the join. You've just added more columns. Okay. Now, I don't really use anti-join, but basically the idea would be I want to find the rows in X that don't have a match in Y. So this might be interesting. So if I go back to my HIV example, and I have rows for census defined places in my X table, and I have all of the providers in my Y table, if I do an anti-join, that would tell me where are all the census defined places where there are no providers who could prescribe PrEP. Okay. And so that would get me down to like 1 or 2 rows that there are no matches in the Y table. And we would say, oh, well, these are very important from a public health intervention standpoint because we need to find out where are the nearest providers to these census defined places. So the anti-join says keep all of the rows in X that don't have a match in Y. Okay. So left join is keep all of the rows in X, no matter what, and find the rows in Y that match. Anti-join says keep all of the rows in X that don't have a match in Y. The inner join says keep all of the rows in X only that have a match in Y. So this one's not going to pad with NAs. So if I had 5 census defined places and this one did not have any providers in it, okay, the anti-join would find only this record. The inner join would find everything but this record. And the left join would keep this record, but you'd have a bunch of NAs right here, okay? Then the last one is full join. And if I have 5 records of data, but I have 30 records of providers, it's just going to end up being like 30 rows. And then everything over here gets padded with NAs. And then the row right here that didn't have a match in the provider data, that would also get padded with NAs. So you can think about full join is often going to result in your data having like chunks of missing values where the values, the records from X didn't have a match in Y. And then, so that's the chunk of missing values over here. And then there's going to be a chunk of missing values over here where the records in Y didn't have a match, or let's see, the records in Y didn't have a, oh, no, I've got it backwards again. So if I've got chunks of missing over here, that would mean the records of Y didn't have a match in X. Chunks of missing down here means that the record in X didn't have a match in Y. So like I said, I'm hoping to bring an expert in to give you a full-on lecture on this so that you don't have to suffer through my blunders. But anyway, so quick example before we go on, and this was how did I figure out that AA was American Airlines, or what did we say, B6 was JetBlue or something? I don't know what these abbreviations are. So what I can do is I can go into the airlines data set and then say, okay, well, I've got my not canceled data set that we had up above, all the flights that hadn't been canceled. And then I want to group by the carrier and the origin, find the average arrival delay. So this is my table. So I've got 35 records that have the different carriers going into the different origins that weren't canceled. But I want to know, what are these airlines? So what is AS? What is HA? I think DL is Delta, VA is American Airlines. So then I would left join on this. So left join means that I'm going to end up again with 35 rows. But in this case, instead of 3 columns, I'm going to have 4 columns. So I see that AS is Alaska Airlines, HA is Hawaiian Airlines, and so forth. And then exercise to wrap up this lesson, find the airports and airlines that have the lowest average arrival delay into Miami. Okay, and next lesson we're going to talk about, I'm going to give you some comparison and go back and like review all of the subsetting rules of dplyr and review all of the subsetting rules from the lists and Tibbles rule and compare them and see how they are different and how they are similar. All right, see you next time.